A programming language uses an evaluation strategy to determine when to evaluate the argument of a function call and what kind of value to pass to the function. For example, call by value, pass by reference specifies that a function application evaluates the argument before it proceeds to the evaluation of the function's body, and that it passes two capabilities to the function, namely, the ability to look up the current value of the argument and to modify it via an assignment statement. The notion of reduction strategy in lambda calculus is similar but distinct. In practical terms, many modern programming languages have converged on a call by value, pass by reference strategy for function calls. Some older languages, especially unsafe languages such as C++, combine several notions of parameter passing. Historically, call by value and call by name date back to ALGOL 60, a language designed in the late 1950s. Call by reference is used by Place, I and some Fortran systems. Purely functional languages like Haskell, as well as non-purely functional languages like R, use by need. The evaluation strategy is specified by the programming language definition, and is not a function of any specific implementation. Strict evaluation. In strict evaluation, the arguments to a function are always evaluated completely before the function is applied. Under Church encoding, eager evaluation of operators maps to strict evaluation of functions. For this reason, strict evaluation is sometimes called eager. Most existing programming languages use strict evaluation for functions. Applicative order evaluation refers to an evaluation strategy in which the arguments of a function are evaluated from left to right in a post-order traversal of reducible expressions. Unlike call by value, applicative order evaluation reduces terms within a function body as much as possible before the function is applied. Call by value evaluation is the most common evaluation strategy, used in languages as different as a C and scheme. In call by value, the argument expression is evaluated, and the resulting value is bound to the corresponding variable in the function. If the function or procedure is able to assign values to its parameters, only its local copy is assigned, that is, anything passed into a function call is unchanged in the caller's scope when the function returns. Call by value is not a single evaluation strategy, but rather the family of evaluation strategies in which a function's argument is evaluated before being passed to the function. While many programming languages that use call by value evaluate function arguments left to right, some evaluate functions and their arguments right to left, and others leave the order unspecified. Implicit limitations. In some cases, the term call by value is problematic, as the value which is passed is not the value of the variable as understood by the ordinary meaning of value, but an implementation-specific reference to the value. The effect is that what syntactically looks like call by value may end up rather behaving like call by reference or call by sharing, often depending on very subtle aspects of the language semantics. The reason for passing a reference is often that the language technically does not provide a value representation of complicated data, but instead represents them as a data structure while preserving some semblance of value appearance in the source code. Exactly where the boundary is drawn between proper values and data structures masquerading as such is often hard to predict. In Maple, a vector is a special case of a table and therefore a data structure, but a list is a value. In TCL, values are dual-ported, such that the value representation is used at the script level, and the language itself manages the corresponding data structure, if one is required. Modifications made via the data structure are reflected back to the value representation, and vice versa. The description, call by value where the value is a reference, is common. Another term is call by sharing, Thus the behavior of call by value Java or Visual Basic and call by value C or Pascal are significantly different. In C or Pascal, calling a function with a large structure as an argument will cause the entire structure to be copied, potentially causing serious performance degradation, and mutations to the structure are invisible to the caller. However, in Java or Visual Basic only the reference to the structure is copied, which is fast, and mutations to the structure are visible to the caller. Call by reference. In call by reference evaluation, a function receives an implicit reference to a variable used as argument, rather than a copy of its value. This typically means that the function can modify the variable used as argument, something that will be seen by its caller. Call by reference can therefore be used to provide an additional channel of communication between the called function and the calling function. A call by reference language makes it more difficult for a programmer to track the effects of a function call, and may introduce subtle bugs. Many languages support call by reference in some form or another, but comparatively few use it as a default, e.g., Perl. A few languages, such as C++, PHP, Visual Basic, .NET, C# and Real Basic, default to call by value, but offer special syntax for call by reference parameters. C++ additionally offers call by reference to const. Call by reference can be simulated in languages that use call by value and don't exactly support call by reference, by making use of references, such as pointers. Languages such as C and ML use this technique. It is not a separate evaluation strategy. The language calls by value, but sometimes it is referred to as call by address. In an unsafe language like C, this may cause memory safety errors such as null-pointer dereferences, and also may be confusing. In ML, references are type and memory safe. Similar effect is achieved by call by sharing, used in languages like Java, Python and Ruby. In purely functional languages, there is typically no semantic difference between the two strategies, so they are typically described as call by value even though implementations frequently use call by reference internally for the efficiency benefits. Example that demonstrates call by reference in E. Def modify p equals 27 hash passed by value. Only the local parameter is modified. Q equals 27 hash passed by reference. Variable used in call is modified. var equals 1 hash value 1. varb equals 2 hash value 2. Modify a hash value 1. b hash value 27. Example the call by address that simulates call by reference in C. Void modify p equals 27 passed by value. Only the local parameter is modified. *q equals 27 passed by value or reference. Check call site to determine which *o equals 27 passed by value or reference. Check call site to determine which int main a is passed by value. B is passed by reference by creating a pointer. C is a pointer passed by value. B and X are changed. Return. Call by sharing, also known as call by object or call by objects sharing. Call by sharing is an evaluation strategy first named by Barbara Liskov al. for the language CLU in 1974. It is used by languages such as Python, IOTA, Java, Ruby, JavaScript, Scheme, OCaml, AppleScript, and many others. However, the term call by sharing is not in common use. The terminology is inconsistent across different sources. For example, in the Java community, they say that Java is passed by value, whereas in the Ruby community, they say that Ruby is passed by reference. Even though the two languages exhibit the same semantics, call by sharing implies that values in the language are based on objects rather than primitive types, i.e., that all values are boxed. The semantics of call by sharing differ from call by reference in that assignments to function arguments within the function aren't visible to the caller. So, e.g., if a variable was passed, it is not possible to simulate an assignment on that variable in the caller's scope. However, since the function has access to the same objects as the caller, mutations to those objects, if the objects are mutable, within the function are visible to the caller, which may appear to differ from call-by-value semantics. Assignments with the function are not noticeable to the caller, because, in these languages, an assignment binds a variable to a different object. Since the rebound variable only exists within the scope of the function, the counterpart in the caller retains its original binding. However, mutations of a mutable object within the function are visible to the caller because the object is not copied or cloned, it is shared. For immutable objects, there is no real difference between call by sharing and call by value, except for the object identity. The use of call by sharing with mutable objects is an alternative to input-output parameters. The parameter is not assigned to, but the object is mutated. For example, in Python, lists are mutable, so def L, append m equals fprint, outputs 1, because the append method modifies the object on which it is called. L equals 1, m equals fprint, outputs, because the statement L equals 1 reassigns a new list to the variable rather than to the location it references, although this term has widespread usage in the Python community. Identical semantics in other languages such as Java and Visual Basic are often described as call by value, where the value is implied to be a reference to the object. Call by copy restore, call by copy restore, copy in copy out. Call by value result or call by value return is a special case of call by reference where the provided reference is unique to the caller. This variant has gained attention in multiprocessing contexts and remote procedure call. If a parameter to a function call is a reference that might be accessible by another thread of execution, its contents may be copied to a new reference that is not, when the function call returns. The updated contents of this new reference are copied back to the original reference. The semantics of call by copy restore also differ from those of call by reference where two or more function arguments alias one another, that is, point to the same variable in the caller's environment. Under call by reference, writing to one will affect the other. Call by copy restore avoids this by giving the function distinct copies, but leaves the result in the caller's environment undefined depending on which of the aliased arguments is copied back first. Will the copies be made in left to right order both on entry and on return? When the reference is passed to the callee uninitialized, this evaluation strategy may be called call by result. Partial evaluation. In partial evaluation, evaluation may continue into the body of a function that has not been applied. Any sub-expressions that do not contain unbound variables are evaluated, and function applications whose argument values are known may be reduced. In the presence of side effects, complete partial evaluation may produce unintended results. For this reason, systems that support partial evaluation tend to do so only for pure expressions within functions. Non-strict evaluation. In non-strict evaluation, arguments to a function are not evaluated unless they are actually used in the evaluation of the function body. Under Church encoding, lazy evaluation of operators maps to non-strict evaluation of functions. For this reason, non-strict evaluation is often referred to as lazy. Boolean expressions in many languages use a form of non-strict evaluation called short-circuit evaluation, where evaluation returns as soon as it can be determined that an unambiguous Boolean will result, for example, in a disjunctive expression where true is encountered, or in a conjunctive expression where false is encountered, and so forth. Conditional expressions also usually use lazy evaluation, where evaluation returns as soon as an unambiguous branch will result. Normal order evaluation is the evaluation strategy where the outermost regex is always reduced, applying functions before evaluating function arguments. In contrast, a call-by-name strategy does not evaluate inside the body of an unapplied function. Call-by-name. In call-by-name evaluation, the arguments to a function are not evaluated before the function is called, rather, they are substituted directly into the function body and then left to be evaluated whenever they appear in the function. If an argument is not used in the function body, the argument is never evaluated. If it is used several times, it is re-evaluated each time it appears. Call-by-name evaluation is occasionally preferable to call-by-value evaluation. If a function's argument is not used in the function, call-by-name will save time by not evaluating the argument, whereas call-by-value will evaluate it regardless. If the argument is a non-terminating computation, the advantage is enormous. However, when the function argument is used, call-by-name is often slower, requiring a mechanism such as a thunk. An early use was algol60. Even though by default Scala is call-by-value, it can also do call-by-name. Today's net languages can simulate call-by-name using delegates or expression less than t greater than parameters. The latter results in an abstract syntax tree being given to the function. Eiffel provides agents, which represents an operation to be evaluated when needed. Seed7 provides call-by-name with function parameters. Call-by-need. Call-by-need is a memoized version of call-by-name where, if the function argument is evaluated, that value is stored for subsequent uses. In a pure setting, this produces the same results as call-by-name when the function argument is used 2 or more times. Call-by-need is almost always faster, because evaluation of expressions may happen arbitrarily far into a computation. Languages using call-by-need generally do not support computational effects except through the use of monads and uniqueness types. This eliminates any unexpected behavior from variables whose values change prior to their delayed evaluation. Lazy evaluation is the most commonly used implementation strategy for call-by-need semantics, but variations exist. For instance, optimistic evaluation. Haskell is the best-known language that uses call-by-need evaluation. R also uses a form of call-by-need. Net languages can simulate call-by-need using the type lazy less than t greater than. Call-by-macro expansion. Call-by-macro expansion is similar to call-by-name, but uses textual substitution rather than capture avoiding substitution. With uncautious use, macro substitution may result in variable capture and lead to undesired behavior. Hygienic macros avoid this problem by checking for and replacing shadowed variables that are not parameters. Non-deterministic strategies. Full beta reduction. Under full beta reduction, any function application may be reduced at any time. This may be done even within the body of an unapplied function. Call-by-future. Call-by-future is a concurrent evaluation strategy. The value of a future expression is computed concurrently with the flow of the rest of the program by one or more promises. When the value of the future is needed, the main program blocks until the future has a value. This strategy is non-deterministic, as the evaluation can occur at any time between creation of the future and use of the future's value. It is similar to call-by-need in that the value is only computed once, and computation may be deferred until the value is needed, but it may be started before. Further, if the value of a future is not needed, such as if it is a local variable in a function that returns, the computation may be terminated partway through. If implemented with processes or threads, creating a future will spawn one or more new processes or threads. Accessing the value will synchronize these with the main thread, and terminating the computation of the future corresponds to killing the promises computing its value. if implemented with a coroutine, as in netAsync, await, creating a future calls a coroutine, which may yield to the caller, and in turn be yielded back to when the value is used. Cooperatively multitasking. Optimistic evaluation. Optimistic evaluation is another variant of call by need in which the function's argument is partially evaluated for some amount of time, after which evaluation is aborted and the function is applied using call by need. This approach avoids some of the runtime expense of call by need, while still retaining the desired termination characteristics.